So let's say we want to know the average height of children, and we're going to draw a distribution. We're going to say every child in the US or in India or any other country, let's draw the distribution for every single kid's height, right? And kids are short. That's why I beat them in basketball whenever I play them. No, just kidding. They beat me. And we're looking at frequency. How frequent is each height? This is, I don't know, what's the shortest? I guess kids come out of the womb and they're like 18 inches or something. So maybe this is like the shortest. Maybe this is 18 inches, I don't know. I'm just guessing. But the point is, here's the distribution of heights for kids for a given country. And it's every single kid. This is the population data. If you want to sample this data, you randomly select, I don't know, 100 children. And, so you're getting a kid from this point right here, you randomly choose a kid from right there, you randomly choose this kid, and you do this 100 times, 100 random kids. Oops. You're more likely to get kids near the center, right? This is the most likely value you get when you start sampling randomly the population. We'll call that value mu. And you average all of these values together. And where is the mean height? Your sample mean is maybe right there. You put those kids back, you select 100 more random children, you get the mean, and the sample mean is right there. You do another sample mean and it's there, another sample mean and it's there, another. And if you plot how frequent the sample means are, well, you never get a sample mean over there because there aren't enough kids at this height to randomly choose 100. I mean, maybe there are, it's just highly unlikely. And odds are you're not going to randomly select 100 kids, all of whom are over here, so you never see a sample mean all the way over here. Your sample means are narrower, right? Maybe something like this. Maybe that's the distribution. And so this is the distribution of the height x, capital X. This middle graph is the distribution of their means, right? Given a sample size of 100. This is the idea of one of the ideas of the central limit theorem. It says how much more spread out is this than this? Well, the difference between the two is 1 over root n, the sample size. More formally, it's the standard deviation in the mean height of your sample is equal to the standard deviation of all heights for all kids in the entire population over root n, where root n is the 100, how big is your sample? 100, right? The way we tend to write this, we call this standard error. And this is just like the big graph's standard deviation, right? Okay, so now we have a different context. So the new context is I'm a graduate student. Apparently can't afford a camera that zooms. I'm a graduate student. I look around my classes and I start to think, I bet graduate students are shorter on average than the adult population in the US, let's say. And I'm looking around my classes, maybe there's a reason, maybe grad students are younger than the general adult population, but whatever the reason, I think grad students are shorter than the population of grad students in the US is shorter than the population of all adults in the US. That's what I think. So we're going to plot x bar, not the height. We're not plotting this distribution. I'm going to plot x bar. So I'm not plotting this. I'm now plotting this littler distribution, but I'm going to spread it out so it's easier to see. Okay. And let's fix that. High quality camera work here. And we're going to make this graph I randomly select a group of, let's just say 5, since it's fewer to draw. I randomly select 5 grad students, and I measure their height, x bar. Little x bar is the height of a particular sample. Big x bar, capital X bar, is the random variable for the mean height of a sample. So little x bar is a particular sample of maybe 5 people. This is all samples of 5 people, every possible sample you might select. 5 is a bad number, that's way too small, but it's easier to draw. And I get my x bar, and here they are. That's the value of x bar. Doesn't really tell me much, right? If that's all I'm looking at, we don't know what conclusion to draw. I do another sample, I get an x bar here. And another sample, and my x bar is here, and then here, and here, and here. And I keep doing this, and if I draw how frequently each x bar is, I get this, right? We imagine I do this infinite times, and this is my distribution. What's the distribution of adults? Well, I get a sample here. Okay, so now I collect a sample of 5 from the adult population, all adults in the US, a different pool, and I get an x bar of here, and then here, and then here, and here, and here, and here. And if I plot how frequently all of those x bars occur, it's like this. The null hypothesis was saying, this is the distribution for grad students. It said there's no difference between grad students and the adult population. This is the alternative hypothesis, which says there is a difference. Grad students are shorter. So that's like, in theory, what the math is doing. It's imagining infinite samples from both groups, grad students and the adult population, and it's comparing. It's like if you just did a single experiment, if you just got one sample, not infinite, and your one sample was right there, can you look at that one sample and conclude it must have come from H1, it could not possibly have come from H0? That's what power is about, that's what hypothesis tests are about, is taking a single sample and inferring which distribution it came from. How could you possibly take a single sample and conclude it cannot have come from H0? How is that possible? Well, under this type of circumstance. Here's H0, here's our sample mean, that's what we get, little x bar. Here's the random variable big X bar for all samples of size 5, all possible samples we could draw of size 5. If this is the situation we're in, X bar is way far from, really far from H0, from mu0, I should say, the hypothesized mean under the null. I mean, this event, how likely is this? Let's say the probability of X bar being, anywhere to the left, being here or less, little x bar, let's say that probability is 0.0001, or 0.01%, right? 1, 2. So if you observe something that the null says is 0.01% likely to occur, I mean, let's say this another way. If the null thinks this observation occurs 0.01% of the time, what the null says is you will never measure an X bar right there. That's what the null is saying. The null is saying an X bar right here is statistically impossible. Not actually impossible, but it's so low it never occurs. So the null says you're never going to measure something right here. You measure something right there, and what do? You reject the null. This is the idea behind hypothesis tests. We walk around the world thinking the null is true. We assume the null is true, right? We walk around, what's the average height of adults in the US? I don't know, but I'll just say 60 inches because it's easy. We walk around the world. We go to the grocery store. We look at 5 random people in the grocery store, and we see their height whoops, drew that one's head on the wrong part of their body. We look at the 5 people and we get an X bar of, 62 inches. And we're not surprised. We don't say, whoa, 62, this must be wrong. No, that's not surprising. That's not unusual. There are deviations from the mean. We walk to the playground and we look at the adults there with their kids. And we randomly sample 5 people. The sample of 5 people from the playground. And X bar is, 57 inches. And we look at this value and we're not surprised. We don't say, oh, this must be wrong. No, there are deviations from the norm. We live in a noisy world where random fluctuation occurs. That's exactly what this plot is saying. H0, mu 0. This plot is saying, yeah, you're not always going to see every sample exactly at 60 inches. Sometimes it's here, sometimes here, sometimes here. And we live in a noisy world. P-values help us find unusual results in a noisy world. P-values help us say, whoa, 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 slow down. You just got something all the way over here. Maybe that's the wrong distribution because an event like this will never occur under this distribution. And if you see something all the way out here, it probably didn't come from this distribution. There's probably some other distribution for that subgroup, graduate students. So that's what p-values do. We walk around in a noisy world. P-values help us find unusual results that tell us to overturn this assumption of the null. Okay. So power is how likely are we. Power is the likelihood of rejecting the null when H1 is true. So let's look at this. Here's power. So here's the true population of grad students. Here's the adult population, right? The true height. Did I say true height? I don't think so. This is the true height of grad students. This is the true height of adults in the US. We can't change those values when we do an experiment. Whoops, can't draw. So I'm drawing 3 graphs, and these should be the same distance apart in all 3, but doing my best. Imagine we conduct an experiment, and the null hypothesis has a distribution like this, and mu1, the alternate hypothesis has a distribution like this. I'm trying to draw these equal width. Then we conduct an experiment, and the distributions are like this. We conduct another experiment, ignore this line, and the distributions are like this. It's the same distance between the two in all cases, but the obvious difference is this is much wider, these distributions, and these are much smaller. So we can't change the difference. We can change how wide the distributions are. What we're plotting here is X bar, right? If we go back, we're plotting this guy here, this littler one, this skinnier one. And what makes this skinnier than the population? Well, this is the mean. So you don't see means all the way over here, because that would require that you randomly select 100 people that are all right in this part of the graph. So the mean is going to be tighter around mu. And how tight is it? Well, that's where the sample size comes into play. So when we plot those X bars, you can get this scenario where it's like super skinny, like on the last page. You just need a bigger sample size. So the sample size changes how likely we are to like if you randomly pick a sample, and what's the sample value? Let's say the sample is just slightly to the right. Here's X bar, right? This is capital X, this is lowercase x bar. And lowercase x bar is the particular sample. And I'm going to mark it right here also, X bar, and right here, X bar. In this scenario, we should draw another set of graphs. Here's the null again. Here's our x bar. Here's the next experiment. Here's the null. Here's our x bar. And here's the last case. Here's the null. And here's the exact same x bar. So let's say we measured we got a sample of grad students. They were only 50 inches, just to keep the math easy. This is 60. That's mu 0. Here's our 60. This is still 50. 50 and 60 for mu 0. So if you measure your 50 inches for the sample of grad students, can you look at this HO and reject HO because this is incredibly unlikely? Probably not. If this is the HO distribution, and it's centered on 60, and you measure 50 inches, under this distribution, is 50 inches so unlikely that you're going to reject HO? Maybe. It's hard to tell. Depends on your confidence level. Where's that cutoff for the rejection region? If this is the situation, and you have such a large sample that the standard deviation, sigma over root n, that standard error, I should have said, is so small that it makes the distribution this narrow, the distribution of means, x bar, for some given n, maybe n is 1,000. Maybe here, maybe this is x bar for n equals 100. Maybe this is the distribution if you only have a sample of 5, right? The larger your sample, the tighter the distribution in theory, according to the standard, the central limit theorem. So if you measure your 50 inches from your grad student sample, can you look at that measurement and reject H0? Yes, because you would never see a measurement like this under that null hypothesis. Okay, so again, this, like, the p-value here might be 0.3, the p-value here might be 0.06, and we don't reject here, the p-value might be 0.0001, and we do reject the null. These are not really the true probabilities. This is just what the null thinks the probability would be of getting 50 inches. The null is wrong. None of these are the true probabilities, but we have to trick the null into thinking that this was a rare event. And yeah, that's what power is asking. Like, what's the sample size, 5 versus 100 versus 1,000, that produces a power high enough to be in this category? Okay, not very eloquent, but that's the idea. So the key fact, though, when you start, like, if this is your experiment where you're going to draw a sample whose size is, I don't know, 50, and that's the theoretical distribution. It's the width of this is the theoretical standard deviation based on a sample size of 50 over root 50. And it's centered on 60 inches, we said, for the general adult population. When you start sampling grad students, here's all the grad students, okay? This video is already too long. There's no time for me to draw all the grad students in the world, but here they are, let's say. All the grad students in, not the world, the US, I limited it. Or, you know, China or India or whatever country you want to pick. Here are all the grad students. You randomly pull 50 and you measure their x bar, their mean height, and you get something over here. And if we imagine repeating, you get 50 more grad students. You randomly pick them, measure their x bar. It's here. You get an x bar right there. Then you do it again. Your x bar is here, then here, then here. The point I want to make is you shouldn't expect, like, if h1 is true, you're not going to see those values centered over here. This is the wrong hypothesis. You're going to see them centered on some other distribution, which we're trying to infer from a single sample. But, so like, it might seem surprising to get something all the way over here, so far away, but keep in mind, when you get that low p-value, keep in mind, it's not actually surprising, because it's actually coming from some other distribution. That's the point I wanted to make. Okay, so let's do an example with an actual calculation. So let's say that the mean height for adults in the US is 60 inches. Let's say the standard deviation for that height for all adults in the US is 4 inches, something simple, right? And you're doing a sample of 100 grad students, and confidence level is 0.05, and we'll make it a two-sided test. So that means H0 says the height of graduate students, mu, is equal to mu0, the value 60. Right? Now, when you do your hypothesis testing, what you do is you write H1 and you say mu is equal to mu1, which is not 60. And then we go ahead with calculating p-values and so on. We're not going to get p-values right now. We're going to imagine the true mu1. You never know mu1 when you start your experiment. But we're going to imagine a scenario where mu1 is actually 50. So the true population height for grad students in the US is 10 inches less than all adults. This is not like the world we live in, but we're pretending. Make the values easy for the example. So what's going to happen? How do you calculate the power in this circumstance? The power of your test. Well, you have selected these values. You chose the alpha, you chose the sample size. And here's what those things do. The sample size, we're looking at the mean given sample size of 100. So among those different options, you're going to be closer to here or here. You're not going to have as much overlap. You've designed the experiment to look like one of these. Maybe it's in between. So let's draw the theoretical null model. Right? You go into the experiment, you walk around the world thinking the null hypothesis is true, and so here's the null value. You walk around the world, you don't expect every sample of n equals 100 to be exactly 60. You expect there to be some deviation. You know how much deviation there should be. It's the standard deviation over root 100. That's the standard error in the sampling mean. The sampling mean, I'm not sure. So anyway, you draw the theoretical null model. Here's H0. You expect that width to be sigma, which is 4, over root sample size, which is 100. Okay, so remember, you start sampling, you draw a single sample, one sample of grad students. And it's probably going to come from like some distribution over here. So you're usually going to get a value in this area. But you don't know that. You walk in, you assume H0 is true, you think this is correct. And you get a sample value, X bar. You go into the experiment with this alpha. So you walk into your door, you walk into the building ready to conduct your experiment, and you already know that if you get a value in this area or this area, you know you're going to reject the null hypothesis, right? You walk in with that predetermined. This is like, that shaded area is 2.5%. this shaded area is 2.5%. And you standardize, right? We always standardize our distribution. So you get some x bar, you subtract mu 0, and what you're doing is you're taking this graph, and you're subtracting, you're shifting it over so that it's centered on 0, and you divide by the standard error. Was it 4 over root 100? And that basically takes this graph and like squeezes it down so that the standard error would be 1. So now we have a standard normal curve, which is z. And we say, what are these two rejection regions, right? What's this value? What height is low enough? What average height, right? You get your x bar. What's the x bar at which you reject h0 because it's too low? What's the x bar at which you reject h0 because it's too high? That's what these cutoffs are. They are quantiles on this curve, and so we could find them in R using Q norm. I'm not even going to standardize. Like, that's the method we've learned. But you could find these quantiles, these values that, lead to rejection. Let's see, this quantile over here is the 2.5 percentile, so that's p equals 0.025. The mean, I'm not worrying about standardizing. The mean is 60. The standard deviation is this is the sampling distribution. This is the distribution of x bars for n equals 100. So in theory, that should have a standard deviation of 4 over root 100, like that. And we get this value, and I'm going to call it Q from the null, H0. What quantile is it? It's the 2.5 percentile, or yeah, hopefully that makes sense, what I just said. Not so sure. Then we do it again, and we find this cutoff. I wrote 2.5% because they add to the 5, but this is the top 2.5%, the upper 2.5%. So when we do Q norm in R, the probability is actually 0.975, 1 minus 2.5. The mean, again, is 60. The standard deviation is 4 over root n. And we'll call that value the quantile from the null. It's the quantile from H0, comma, this is all supposed to be a subscript. What quantile was it? It was the 97.5 percentile. Okay, so we know the rejection region, and we could literally plug this into R and get the value. Maybe that's worth doing. So I'll just do this in R and then report back. So the first one is Q norm, probability is 0.025, the mean is 60, and standard deviation is 4 over 10. And that's 59.2, we'll just call it 59.2. So this height, if your sample mean, if your graduate students have an average height less than this, you reject the null, because this is way too rare to occur with a sample of 100 people. If you get a value, let's calculate this second one. So this was 59.2. The second one is going to be, I should be showing what I'm doing in R, but it's going to be tough to do. It's just, I'm just typing this. This is 60.8. So this cutoff, 60.8 inches. So if your grad students have a height taller, an average height taller than 60.8 for the 100 grad students, that's so extreme you reject H0. Okay, so now we need to say, well, how likely are these values? How likely are we to measure an average height less than this or greater than this? Because remember, like, we start sampling grad students, and we're gonna get values over here where h1 is, we're not sampling from h0, we're sampling from the true x bar. Let me draw it down here. The true x bar for grad students is something like, I'm going to put it closer, something like this, right? And so if I compare the two, 59.2, let's mark 59.2, it's like somewhere here. Oh wait, this is supposed to be 50, so 59.2, let me try again. I draw it actually to scale. So here's 50 inches, that's the true mean we said. Here's 60, I'm going to exaggerate and put 59.2 right there. And then what was the other value? 60.8. And I'll exaggerate and put 60.8 right here. I chose a sample too large to make the drawing realistic, but okay, so here's H1. This is the distribution we're actually pulling from. Yeah. And we want to know how likely is it. We said reject H0 if x bar is less than equal to 59.2, whoops, or x bar greater than equal to 60.8, right? When we look at the null, which is wrong, these are the extremes that lead us to reject. That's what we mean by like, oh, this is so rare, the null can't possibly be true. Down here, we're looking at how rare these events really are. I mean, like, less than 59, that's usually what happens. Like, less than 59 is all of this area. Greater than 60.8 is so small, that's going to be negligible. I mean, the graph, like, maybe the graph extends like this and gradually goes down, and there's some tiny area to shade in, but, you know, that's going to be negligible. So we're calculating the power for this two-sided test, alternative hypothesis. We're doing the calculation for sample mean, not for proportion, but here's what this is. The power is the probability under the true alternate hypothesis, the actual true probability of rejecting the null, which is the probability that x bar is less than or equal to 59.2, plus the probability, the true known probability that x bar is greater than or equal to 60.8. So this is going to be just p norm with a quantile of 59.2. The mean now is, we're talking about what's the probability of getting an actual x bar that leads to rejection. So we're sampling from the actual alternate hypothesis, which has a mean of 50. And the standard deviation, when we do means, testing two means, it's the same standard error for x bar h1 and x bar h0. They have different means, but they have the same standard error. Like when we draw, did I draw them on the same spot? When we draw the alternate hypothesis and the null hypothesis, we're drawing them the same width. I think it's possible to do tests where they're not the same, but I don't know how that works. So anyway, that's sort of like an assumption when we do this type of calculation, this problem. The standard deviation of x bar, which is the standard error, is going to be also 4 over root n, what we had above. Yeah, that makes sense, right? Because okay, yeah, that makes sense, because they're both positing, they're both saying, well, maybe this doesn't make sense. Like, they're both using sigma over root n, and so maybe they would not be the same. It seems like it would be possible. Okay, it seems possible to have scenarios where you think grad students have less variation. Like this seems possible. I should have labeled this mu. And this is the alternate model, this is the null model. Yeah, it seems like it seems possible to be in a situation where you, the experimenter, believe there's less variation in grad student height than there is in the adult population, but that's not what we're doing in this test. In these sorts of scenarios, we're assuming that the two graphs have the same standard error. Okay. So we do this, and now we're calculating this area. We're saying how likely is it that the actual sample mean, which comes truly from H1, how likely is it that it counts as extreme under the null? And that's what this first part gives us. It gives us the likelihood when we start sampling and we get something here and then here, or maybe we get a sample and it's here or here, how likely are we to get something to the left of this value, which leads to rejection, or how likely are we to get something to the right of this value, which also leads to rejection? Well, to see how likely, we don't look at H0, we look at the true distribution where those x bars come from. And that's what this is. That's what this graph shows, given n equal to 50. So, so we found this probability, the probability of x bar being less than this. We need the complement to get, since this is greater than or equal to, we need to get the complement. So p norm q equals 60.8. And then the rest of this is the same. The mean is 50. The standard deviation is 4 over root 100. And we literally just plug this into R, and it gives us the power of the test. But like at the core, and by the way, this is, sometimes people say you only need to do one of these and the other is negligible. And now we can see why that's true. Like the null model was here, right? And one of these tails is going to be so far away from the true mean that you're never going to see data out here, and you can ignore that probability. You could ignore this and focus on the other piece. So that's, sometimes we say that only one of these is non-negligible for a two-sided alternative. But at the core, right, when we're talking about power, we're imagining the situation. This won't always be true, but we're imagining the situation where there is a difference. And we're looking at the experimenter, watching her do the experiment, and we're saying she's going to reject H0 if she gets a value over here or over here. And we're watching her conduct the experiment, and we're saying, how likely is she to reject this distribution and realize the data is actually coming from this distribution? Right? Realize her x bar is actually coming from this x bar distribution, not from this x bar distribution. And that's what we're asking when we calculate power. We're saying, for the given confidence level, and this is a two-sided, how likely is she, when she starts sampling this, she's going to go sample this distribution, she thinks it's coming here from here, but it's actually coming from here. And if this is really the true distribution, how likely is she, if this is the true distribution, and let me trace this down, how likely, and trace this down, how likely is she to get a value over here or over here? And I can't even shade that area because it's so low. And that's what the power tells us. It's the probability, using her null when she looks at the null, it's the probability that she collects an x bar that then falls into this region or into this region. Her x bar is coming from h1, but she's putting it on the h0 distribution and evaluating whether that x bar must have come from something else besides h0. So that's what power tells us. Formally, it's the probability of rejecting h0 given that h1 is true. And again, as the experimenter, we can't control the effect size, the difference between these. All we can control is our sample size, which changes how narrow these graphs are. And it changes how likely we are when we randomly sample this distribution. If our x bar has a tighter distribution, then and there truly is a difference, then we're more likely to get a value which does not make sense under this distribution. And that's why a big sample size increases the power.